Okay, so now we're going to look at another example of the exponential family, a member of the exponential family, it's like which is the discrete distribution. Okay, so you have distributions of discrete random variables. A single discrete random variable x over some big set x, which takes values from 0, 1, all the way up to n. Okay, so if you recall, it's like because of the fact that these probabilities associated with each of these possible outcomes, each of these possible n plus 1 outcomes, right, is non-negative, it's like, and it sums up to 1, they form a probability simplex, right? So this forms what is called a probability simplex, which we denote by S sub n, right? And then a distribution, okay, P consists of a set of probability distributions, P0 to Pn, right, is represented as follows. Okay, so you have P of x is equal to the sum from I equals 0 to n of Pi, the Dirac delta function, sorry, the Kronecker delta function, delta I x, where delta I j is equal to 1 if I is equal to j, and 0 if I is not equal to j. Okay, all right. So as before, it's like we want to show that this is a member of the exponential family, right? Or is an exponential family. Okay, so we show that Sn is an exponential family. Okay, so how do you do that? So let's take the log of this. So log of px is equal to the sum from I equals 0 to n of log pi delta I of x. So I can write this in the following way: sum from I equals 0 to n of log pi delta I of x plus, all right, so I'm going to sum from 1, I'm sorry, instead of 0, and then I'm going to have log p0 delta 0 of x. Okay, so what I can do is I can add log p0 to all these other terms, right? And then subtract it off again, okay? And if I did that, then, oh, okay, actually what I should do is I should subtract off log p0, it's like from all these terms, and then I add log p0, it's like with the delta i's from I equals 1 to n, it's like to this term. And the net effect of doing that is to give me the following. Maybe let me do this in a clearer way. You know that if you have a function which is 1 for all possible values 0 all the way up to n, I can write this as the sum from I equals 0 to n of delta I of x. Okay? So I can take this, multiply by log p0, and add it to this thing, and then subtract it off again. Okay? And then what would happen is that when I subtract these terms, the log p0 term, I get the sum from I equals 1 to n log pi divided by, sorry, log pi divided by p0, right, times the Kronecker delta function, right, and then this term just becomes log p0. Okay, right, okay, so, and it comes from this identity that 1 is just the sum from 0 to n of the delta functions, the Kronecker delta functions. So if I add the sum from, yeah, okay, if I add, it's like log p0, it's like delta 1 all the way up to log p0 delta n, it's like that term just becomes log p0, right? And then I've subtracted off the log p0 delta 1 to delta n, it's like here, and I combine the two logs into this log of a quotient. Okay, anyhow, so that's what you get. Okay, so with that I can think of these Kronecker delta functions as the h functions which are used in the exponential family. And then this is the k function basically, right, which okay. Okay, so we introduce new random variables. Let's call it xi, and then xi is equal to hi of x, which is delta I of x, and I goes from 1 to n. And then you have new parameters, excuse me, which are these log pi divided by p0 terms. All right, so the theta i's, theta super i's are log of p sub I divided by p sub 0. So with that, I can write this distribution now. So we can write p as the following. So p of x theta is the exponential of the sum from I equals 1 to n of theta I xi minus phi of theta. And then the cumulant generating function is given as follows. Okay. Right. So phi is minus log p0, which is log of 1 plus the sum from I equals 1 to n of the exponential of theta I. All right. Okay, so so we just use this definition. It's like in the fact that yeah, and use the fact that the sum of the pi's from I equals 0 to n equals 1, right, which is normalization condition. And the expression for the theta i's, it's like in terms of pi's and p0s, right, to rewrite minus log of p0, which was that normalization condition, normalization factor which we had from before, in terms of the variables theta I. Okay, and then as before, you have that the dual coordinates are the expectations of the HIs. Okay, so the dual affine coordinates are eta I is the expectation of HI of x. Okay, and because these are just the delta functions, the canonical delta functions, they're given by the PIs. Okay, all right, so this is the convex function, and then there's the convex dual of it, right? So the dual convex function is the negative entropy. Right, so psi eta is the sum of eta I log eta I plus 1 minus sum eta I log 1 minus sum eta I. And then the point is that if you use this dual convex function, you take the Legendre transform, you map back from the PIs, it's like to the original coordinates, the original set of affine coordinates, which are log pi divided by p0, right? So as we expect, if theta is equal to the gradient of psi at eta, and then theta I is equal to the log of eta I divided by 1 minus the sum of eta I. Right? Okay, so again, that demonstrates that the set of discrete distributions, it's like on some sort of discrete random variable space, right, is the exponential family, it's I guess we would expect. Okay, so let me just stop here.